All right, let's look at the thing that I promised, the limit as x approaches 0 of sine x over x. First we'll look at the intuition, then we'll look at a kind of a false start for how you're not going to prove it, and then we'll look at how you could actually prove the result. If we look at the two pieces of sine x over x as separate functions, here I've got sine x in red and y equals x in blue. Pretty different functions, but I want you to notice that where we're interested in finding the limit, which is really close to 0, if we zoom in very close to 0, the functions are virtually indistinguishable. Which one is that one? Which one is this one? They both look like y equals x. So you might guess, based on that when x values are really, really small, really, really close to 0, sine x divided by x should be very close to 1. It should be approaching 1. And we can verify that intuition by kind of graphing here. Here's what sine x over x looks like, and indeed it does look like that it approaches 1 as x approaches 0. Alright, I suggested that we could prove that this was true using the sandwich theorem. And before we had pretty straightforward applications of the sandwich theorem. For example, this guy. Here I have x times sine of 1 over x. It looks like the oscillations here are getting smaller and smaller and smaller. So as x approaches 0, x times sine of 1 over x should also approach 0. And this was very easy to show. We can find a function that bounds it from above. So this function is always smaller than, let's do absolute value x, and it is always larger than negative absolute value x. And the absolute value x's have a very obvious limit, and so using the sandwich theorem we can show that they are forcing this blue function in the middle to have a limit of 0 as x approaches 0. Alright, well let's try and do the same kind of a thing for this sine x over x function. I think the first thing that would occur to us to do is sine x over x is less than or equal to 1 over x and is greater than or equal to negative 1 over x. Alright, that's definitely true. Does this really help us? Even though it's sandwiched, this doesn't really help us because these two limits aren't defined. As x approaches 0 from the left-hand side, you get a different value than when x approaches 0 from the right-hand side. So because these two limits don't exist, you can't sandwich a limit between two non-existent limits. So that approach has just failed entirely. Just looking at the shape of the graph, one thing that occurs to me is it kind of looks like the cosine graph. So let's see how they compare. Alright, so it looks like the cosine graph maybe bounds my graph from below. What's an easy function that always bounds my graph from above? Well, it seems like the easiest function is maybe just the constant function 1. So now I've found two simple functions, 1 and cosine, and they really seem to be bounding my function. Although, it's not totally obvious. I would definitely want to come up with some further justification, maybe, that sine x divided by x is always larger than cosine x. So a really helpful thing to do is to use geometry and our geometric intuition to try and justify the functions that are doing the bounding. Because I know trig functions involve the unit circle a lot, let's throw a triangle on there. Let's call this angle x. And let's try and see what we can measure geometrically about this circle that might let us get a sine x over x. Alright, well one thing to notice is that the length of this arc right here is equal to x. Here's why. Let's think about what the entire circumference of this unit circle is. So that's 1, and this is 1. The entire circumference is 2 pi. If I want to know what percentage of the circumference, if I want to know what percentage of the entire circle this angle is, that's going to be x divided by 2 pi. Now, if I multiply that percentage by the entire circumference, that should tell me how long just that sector is, the length of that sector. So, if I multiply that by 2 pi, I've got that the length is just x, which is one of the nice properties about radians. Alright, let's find something that is definitely larger than this arc length, and something definitely smaller than the arc length. So, if I draw a straight line down from here, that should definitely be smaller. If I draw a straight line up from here, that should definitely be larger. How can I describe the lengths of those things? Well, the length of this guy is just sine x, just by SOHCAHTOA. The length of this guy here should be tangent x. The reason why is tan x gives us this side divided by that side, but this side is the radius, which is just 1. All right, so this will let us write an inequality that we know is true based on the geometry of this situation. I know that sine x must be less than or equal to x must be less than or equal to tangent x. All right, well, this isn't going to let us sandwich anything yet. So let's try and manipulate it a little bit so that we can get a sine x over x out of this. I need my sine x divided by x to be in the middle here. It needs to be sandwiched. So let's divide everything through by sine x. So sine divided by sine is 1. X divided by sine is x over sine. Tangent is sine over cosine. So when I divide it by sine, the signs cancel, and so now I just have 1 over cosine, or secant. Let's take reciprocals, but we've got to be careful when we take reciprocals that we pay attention to which direction the inequality is going. So if this side is larger than that side, if I'm going to write reciprocals, that's like saying 1 divided by the old thing. So if this side was larger than that side, 1 divided by a larger number should be smaller than 1 divided by the smaller number. So actually the direction of this inequality should reverse. And now we've got to sandwich this direction. Aha! We recognize this from the graph that we had before. We have sine x over x as being bounded below by just cosine x and above by 1. So using just straight geometry, we verified that the functions that looked like they were bounding actually are bounding. All right, from here on out, you should be able to do it. So we can say limit x approaches 0 of 1 is greater than or equal to limit x approaches 0 of sine x over x greater than or equal to limit x approaches 0 of cosine x. This is just 1. This is also 1. Therefore, the limit that we care about by the sandwich theorem must be equal to 1. So remember in the future that if you want to try and apply the sandwich theorem, it's sometimes helpful to make a geometric construction so that you can actually compare things about the construction. I've given you a proof in terms of the lengths of these lines and arc lengths. You could redo this exact same proof using the areas of the triangles here and the area of that sector. In other problems, you might need to construct a different shape and compare different measurements of that shape to do your sandwich.